long something's been dead for. If anyone's heard of carbon dating, that's basically the same type of situation here. Okay, so if you're trying to figure out how long someone's been passed for, or if you're trying to figure out how long a drug has been in your system, okay, or when is it going to be out of your system, this is how you would do it, your half-life. Every drug has a half-life, and people use it all the time when it comes to the medical field. Okay, so Simon is studying for a big test and is trying to stay awake, which I'm sure some of you did drink some energy drinks in the past, which are awful for you, by the way, and I would recommend not drinking. They're really bad for your heart. But he drank a 12-ounce can of Big Buzz Energy, and the drink contains 80 milligrams of caffeine. Okay, so that's my starting amount. When I drink it, I now have 80 milligrams in my body. Okay, that's a lot of caffeine. He is wondering how long the caffeine will stay in his system if the caffeine has a half-life of 5 hours. Okay? So a half-life of 5 hours. That means every 5 hours it decays by a half. So a half-life is the amount of time it takes a substance to decay by a half, which is basically what I just said. So if you have a highlighter, I mean, that's a definition. That's supposed to be a highlighter. Okay. How much caffeine remains in Simon's system after 5 hours? 40, right? Because, again, if it decays by a half, we're going to divide by 2 or multiply by 1/2. So we're going to do 80 divided by 2, which gets me 40 milligrams. That means in 5 hours, he will still have 40 milligrams of caffeine, which is still a lot. Okay, so if you're if you go home after school, and you get home at like 4, and 5 hours later is 9 o'clock, and you still have 40 milligrams in your system, you're not going to bed. I mean, I don't know if you can. I wouldn't be able to go to bed at 40 milligrams. What'd you say?
I would.
Yeah, I would not be able to fall asleep with 40 milligrams. I'm not sure.
Around 40.
Around 40, you think?
I just hit a mouse to this point.
Oh, it's awful. Don't do it. Okay. No, like if you drink too much of it, your heart can actually like enlarge. It's really bad. I know someone that actually passed from drinking them all the time.
My brother, big heart.
That means you love more.
No, like it's bad as in like for your
My
blood.
brother would drink a lot because he was on some construction, so he like has to wake up early. Yeah. And now it's like his breakfast.
It's
Like,
29
he
milligrams.
shares that as lunch, and one day he was driving home, and his heart his body was shutting down, and we had to take him to the hospital.
Yeah. So good story. Hannah was just talking about how her brother had to drink energy drinks in the morning because he would get up and have construction jobs, or was it construction jobs? I totally missed that. And
You need a bigger heart.
yeah. Anyways, they had to take him to the hospital because of the heart issues. Because if you drink too much of it, it's actually really bad for you. Anyways, let's move on. So after 10 hours, it's really bad for your heart. After 10 hours, how much would you have? You'd have 20 because I would do 40 divided by 2, which would get me 20 milligrams. Okay, so this is 10 hours and this was 5 hours. Explain your reasoning. Okay, I'm not going to explain it, but you should know that we're dividing by 2 each time because a half-life is, again, it decays by 1/2 or multiplies by 1/2. So, what is the initial amount of caffeine in Simon's system? 80. So that's 80 milligrams. That's how much I drank right away. And what did you look up, and how much was it for a Coke?
29.
20. So think about that. If a Coke has 29 milligrams of caffeine, this has 80. That's a pretty big difference.
How much does a mouse do?
We'll look at that up later. So at what rate is the caffeine decreasing in a system? How much each time is it decaying? A half. So that's going to be 1/2. So 1/2 or 0.5 every
86.
5 hours. Okay, that's the rate of decay. So every 5 hours, I am decaying by 1/2. All right, so now this is kind of leading to our formula here. You were given a formula in science. In science, you did not have the H. You just had the T, and you had to figure out and manipulate the problem in a lot of ways. However, I'm going to give you a much easier formula to work with. Write an exponential function to represent the amount of caffeine remaining in Simon's system after any amount of time. So, if you want to find out in like 10 hours or 20 hours how long something is in your body, you can use this formula. What is happening? I really get distracted when people talk when I talk. So our initial amounts here. What was our initial amount? 80. That 1/2, people ask all the time, where'd the 1/2 come from? It's part of the formula because it's a half-life. Okay, you could use 0.5. Sometimes 0.5 is easier to work with. It just depends on what you're doing. So time. We want to leave time alone when we're writing a function, so the t is going to remain up here. But we know what our half-life of caffeine is in the situation. What is it? 5. Okay, so that's our function here for Simon.
So we need to figure out what T is.
Yes, well, we're not going to figure out what t is. We just wanted a general function that we can put in any time in the world that can figure out how much is still in the system. So let's actually do that. How much caffeine remains in Simon's system after 2 hours? So t is 2 here. And let's go ahead and plug this into your calculator. You will be able to use a calculator on this part. Now again, some of you might have not a fancy calculator and have to put this in parentheses. It just depends on what kind of calculator you have. But I want you to try that out. Tell me how much is left after 2 hours.
Make sure you know how to plug this in, guys. If you're not getting the right answer, call one of us over. We'll come over and check how you plug it in.
That's 60.62.
Yep.
What?
I know. What'd you get?
60.63.
Don't forget your units. Okay. Now that makes mathematical sense because we talked about earlier, a half-life would be 40. That means 5 hours. Well, if we're between 0 and 5, we should be higher than 40. So make sure you kind of understand the situation, what's going on. If a half-life's 40 and it's 5 hours, then we should have something more, which we do. We have 60. Okay, so I want you to try this one. Kendra suggests that she can calculate the amount of caffeine remaining by rewriting the equation as this. Is she correct? Just take a minute, if not 30 seconds, with your group and see if you can tell me why. I'll tell you she's incorrect, but I want you to tell me why she's incorrect. Why can't she do that? Why can't she have that function compared to what we have right now?
Bring out the 1/2 part.
Yeah, so a lot of you had some good thoughts. So kind of looking just up above here, what Kendra is doing is she's doing 80 times 1/2. Well, rules of exponents and rules of operations, order of operations says we must apply the exponent before we can multiply. We can't do that. So no, again, orders of operations. Order of operations. Order of op. Okay, so 80 to 1/2 to the t over 5, we can't do that. We can't multiply 80 times 1/2 because this must be done first before you can do the 80. And that's just rules of operations.
So like the way she's doing it, should like if it was like actually 40, we would have to put 10 instead of 5 because it was like 40 milligrams after 10 hours, not 5 hours. Or does that not change?
I don't know if that would work every time. I have to think about that. But
Because it doesn't get to 40 milligrams till like.
you're right. But I think it was just kind of talking about why Katie can't do this. So Katie did 80 times 1/2, which got us 40, but we can't do that first. We have to do the exponent before we do anything. Okay, so moving on to 6. Suppose that Simon is taking an antibiotic that extends the half-life of caffeine to 8 hours. So now, again, when you're talking about any kind of drug, certain drugs prolong that half-life. So antibiotics are a huge one. You take an antibiotic, it could make something defective. It could prolong how long something stays in your system. Okay, that antibiotic, it happens a lot. Antibiotics tend to change either the half-life or just make something defective. If someone's on, okay, I'm not in health class, but if you're on birth control and you take antibiotics, you no longer have birth control in your system. That's just the way it works. Really, welcome to health class. Okay, so anyways, just kind of a random fact, at least you learned something today, right? But that's why, okay? Antibiotics do things to certain drugs that can either make them defected or decay slower. So, suppose that Simon is taking that antibiotic and extends the half-life to 8 hours. Write the function B of t that models the situation. So, same type of formula here. I'm still going to have my initial amount of 80. I'm still going to have that 1/2 that's in every single half-life problem. I'm still going to have the t, but now what's my half-life here? 8. So the only thing that changed was in purple. Everything remains the same as before, but now instead of 5 hours for half-life, we have 8. Because that's what antibiotics do sometimes. They prolong something. Okay, half-lives are pretty cool because if you're in the medical field, you could, if someone comes into the ER and you're trying to figure out how long something's been in their system, you could do that. Now, fill out the table for each function. Here is our original, and here's the antibiotic. Here's the original, and here's the antibiotic. We're going to look at both of them. Our initial amount for both of them is 80. And again, initial amount is 0 half-life, so we should know that. For our first one, when 1 half-life went by, because it was 5 hours, where were we at? 40. Okay, fill in the rest of that chart. Okay, we've already did 2 of them. We did the next one even too on the first page. We're kind of just putting it in chart form now. So take a second. Don't do the next one because it's a little different. Again, because each one of these, our half-life is 5.
So are we? I'm confused on how we got
So because the half-life is 5 and it's going by 5s, we can just divide by 8.
so
Or we can divide by 2. Yeah, and then divide by 2, and then divide by 2. Okay, check your answers for the first one. The second one's a little different because we don't know our half-lives because look at our chart. Our chart is not in terms of 8. Our half-life is 8. That means we're not doing exact half-lives here. They're a little different. And if you notice here, we are going by 5s in the top one. And that's why we were able to tell me the exact half-lives. So we have to look at this one. Now, the only way to really plug this in, or to get your answer, is to plug it in. So for each one of these, you have to actually plug it into your calculator. So 80 with our 0.5 or our 1/2 to the 5 over 8. So put that in your calculator, and that's what you should get on the top. I'm going to do the first one with you. So when you put in your calculator, you should get around 51.87. There's no way, you can't just divide by 2 because they're not exact half-lives. 5 is not 8. If this was 8, I'd say yes, you're good. Well, you're not. You're at 5. So if you can imagine, it's not a full half-life. Does anyone know, kind of make some valid reason of why it should be 51 at least, or even somewhere around there, based off of what you know about half-lives? So our half-life's 8, right? That's smaller than 8. So it should be bigger than 40 because it's going to be bigger than a 1 half-life. Okay, so because 1 half-life is 40, which we already figured out, and because we have 5 here, it should be a little bit more. So just in your brain kind of understanding what's going on. Now, in order to find out how many half-lives have gone by, you just have to do this 5 and divide it by 8. So we put 5 divided by 8, and what do you get?
33.
What'd you say? 0.625. Okay, you could just leave it as 5/8 too. You don't even have to put it as a decimal. So here, it would be 10/8, or you can reduce it. Doesn't matter. Okay, so that's how you find out how many half-lives have gone by, is taking the time and dividing it by the half-life. Okay, so here would be 10 divided by 8. So fill in the rest of the chart. You have to plug these ones in. There's no quick way. I'm not giving you half-lives.
that's the number of half-life cycles we've gone through, is 10 out of 8, which is one cycle and part of another one. Does that make sense? Yeah.
When you're done and when you're done, only check up on the board. I'm going to leave them in fraction form because fractions are easy for me to do in my head compared to trying to do decimals in my head. You can go ahead and plug mine in and you can see if your decimals match. Again, you could have used decimals there. I just don't have a calculator in my brain. I have fractions in my head. So I reduced. Because again, technically, this is 10 over 8, which reduces to 5 over 4. So that's how I got that. You could have used a decimal. Again, do 5 divided by 4 in your calculator, and as long as you got that same decimal, you're fine. Okay, so either one works. We'll accept the decimal or the fraction. Either one's fine. Okay, now let's analyze both of them in a graphing calculator. So again, you need your graphing calculator out. Use the table feature of the graphing calculator to analyze both functions. After interpreting each function, approximate how many hours it'll take for the caffeine to remain in the system to be about 1 milligram. So go ahead in your calculator and type that into your graphing calculator. Go to y equals. Type both of them in. Type both of them in. Your functions for both of them. Come on. I'm going to start taking it. It's getting to a point where it's being obnoxious. You should be going to y equals.
And then in the second round, we're going to put this in.
You may need to change your window. Sometimes I like to use 0.5. 0.5 is a little bit easier for me.
And then just graph it.
And then x over.
You will need to change your window, guys, so just mess with it.
So here's what my calculator looks like. I changed my view. Oop, that looks awful. There you go. Okay, then I'm going to go ahead and press graph, and we're kind of just going to look at this and see what it looks like. What happened? I can. So, I know that we don't have t in our graph. Hold on, mine's thinking. Takes a second sometimes. Come on. Okay, that's what mine looks like. We don't have t, but we have x. Any variable is going to be just fine, as long as a variable. Don't put in like 10 over 8. We want to know any of them. So I'm going to go to my window, and I'm going to make it something around like 50. Okay, if you look at your chart, it's going to be in the 50s, maybe even make it 100. It really doesn't matter. So as long as you're up there, I'm just going to do 100 and 100. I'm going to go by tens. Again, you can change your window to whatever you want. I'm just doing this for me. Oops. Let's see what this looks like. Give it a second, it's thinking. Okay, that's what that one looks like, which is our original with a half-life of 5. And the red one is with the half-life with the antibiotic, which was 8. Okay, so if you look at the graphs, which one of the questions we'll ask, we'll explore that in a second here. But it wants you to find where it's somewhere going to be at crossing here, or 1 or less than 1 milligram in your body. What did you guys find when you went to your table? So when did you find that y was equal to 0 here? It's going to take me forever to scroll down on this. That's when x is 0. But I want to know when y is about 1 or negative, or sorry, 1 or 0.5 or 0.8. So I'm going to go all the way down. I'm scrolling down right now.
It might take a long time if you know the shortcut. If you have an idea about where it might be, you can always hit second window, go to table set, and you can put in an X value and automatically jump to your table when you go to your table to that X value.
I'm scrolling down and trying to find 0. Did you see 0 yet for y? But I'm getting close. Yeah, so let's go all the way down, but we're looking less than 1. When does it start becoming less than 1? I'm going to keep looking. So I'm showing you what my brain is doing. All right. So for this blue one, the blue one is without the antibiotics. Let me scroll back up. Hold on, I think I just confused the calculator.
Mine was 3 to 2. I think. You can't be in the Y. You have to go over to the X. Arrow down.
I can't do anything right now, so. Come on.
How do you like restart your show?
There we go. Okay, I'm going back. I'm going to show you what I mean by this. Look, right here. When does it start becoming less than 1? Around 32. Okay, that's going to be between 31 and 32 hours. That's without the antibiotics. So between 31 and 32, that's not how you spell it. Between 31 and 32, that was that A of T. That's the original with the half-life of 5. Now let's talk about when we had the antibiotic. So again, I'm going to go back to my calculator. I'm trying to find when it's less than 1. Not 70, but it's going to be
78.
not 70. It's not in the 70s. Let's kind of look. That might be where it's 0. Close to 0. I'm looking for when it starts becoming less than 1.
Oh.
There we go, right here. Do you see, at 51, I am now less than 1 milligram in your body. I'm 0.9. Okay, that's less than 1. So around 51, right here in red, is when we became less than 1 milligram in our body. So it took 51 hours. That's a lot of time for something to become less than 1 milligram in your body. So about 51. I forgot my hours. Sorry. So let me explain to you what we just did. I know that took a little bit because you're getting used to the calculator and working with that kind of question. So it says how many hours will it take for the caffeine to be less than 1? Because here's why I asked you that question. What do we secretly have at that x-axis that will never become 0? Yeah, that horizontal asymptote. So something really never technically leaves your system. It's just really small to a point where it's untraceable. It never becomes 0, ever. Okay, so caffeine, when you drink it, it never technically becomes 0, but it's so close to 0 that it's just untraceable. Okay, it's kind of crazy how that works. So, 9, what generalization can you make about the effect of larger or smaller half-life substances? So when we look at our graph here, I'll go back to my graph just to show you. Mine's colored, so it might be nice to look up. The blue one is the original with the half-life of 5. The red one is the one with the antibiotic where the half-life is 8. What kind of generalization can you make about the difference of half-lives here? What happens with the graph? I'll ask you this question. Does a smaller half-life decrease faster or slower than a larger half-life? What'd you say? It does decay faster. Very good. So what do I mean by that? Let's put that into words. So the larger the half-life, oh my God. It takes longer to decay. So again, if my half-life was 10 now, it took 10 hours to decay. It's going to just take you longer and longer and longer to get out of your system. Again, every drug, every element, every chemical, it all has a half-life. You can even look it up online. Okay, if you're trying to find the half-life of caffeine, you could probably figure that out online and try to do some of these problems. We're just going to do one of these questions and talk about it. We're just going to do A and the rest we're going to cross out because it actually has to do with a different chapter, which we haven't done yet. Last year we did that chapter before this, so we kind of just forgot to take it out. So, an adult takes 400 milligrams of ibuprofen. I'm sure you guys have all taken ibuprofen at some point in your life. If not, understandable. Each hour, the amount of ibuprofen in a person's system decreases by 29%. So, every single time, each hour, it decreases by 29%. Is that a half-life problem? No, because in order to be a half-life problem, it must decrease by what? Half, which is 50%. So no. Half-life decreases at a rate of 50%. Okay, and the rest of the time will be yours. You should be able to finish your homework before you walk out the door. Everyone in
We
first
have
hour
about
did.
20 minutes here. You should be able to get this done. Remember, graphing, ladies and gentlemen, you will be required to do on any assessment without a calculator.